عرض سلام دارم خدمت دانشجویان عزیز. با یک جلسه دیگه از درس Embedded System Design در خدمت شما هستم. Hello students, I hope you will be okay. We want to have another session about the Embedded System Design with VHDL. And now at first please inform me about the last topic that we speak about it. Thank you one more. Okay, we speak about the Fpga structure. Now we want to speak about the other things. I want to know if that did we speak about the CLB configurable logic block in Fpga? Let me to share my screen at first, and then we start our speaking about the course. Okay, then we speak about the Fpga structure. Hello. Let me to this. Okay, we start speaking about the Fpga structure, and Fpga structure is divided into three main parts. The first part is the I/O cells. The second part is interconnection resources, and the third part is logic blocks, or we call them configurable logic blocks. We take entity just description. Okay, then we speak about the Fpga structure. Is it right? I can pass through this, yes? Okay, I think let me to speak about the configurable logic block very fast, and then I can go to entity description. As I told you, the I/O cells, it means the cells that can be input or output of the system. Interconnection resources, really they are 6 switches. Each switch is a connection between one part. For example, we have 4 wires up, down, right, left, and we need 6 switches to have a full connection. For example, a connection between up wire to down wire, a connection between up wire to right wire, a connection between up wire to left wire, and etc. And the other part is about the configurable logic blocks, the logic blocks that implement all logic functions, and we want to speak about them. I maybe told you or not that each logic function is really, for example here, each logic function can be stated by a truth table. For example, here we have a truth table with, like this, a truth table here, for example, with 3 inputs and 1 output here, with input A and B and C, and the logic function F. Okay, about the truth table, we know that we have 8 states or 8 conditions. For example, here 0, 0, 0, 0, 1, 1, 1, 1. It is the condition for the A. And for B, zero, zero, 1, 1, 0, 0, 1, 1. And for C, zero, 1, 0, 1, 0, 1, 0, 1. Okay, we have 8 states or 8 conditions here. And we know that for the logic function, we have a special value in each condition. For example, we can write these conditions here in the truth table for simplifying the logic function. For example, we may have 1, 1, 1, 0, 0, 0, 0, and 1. Okay. Then we can see that we have a truth table with a logic function f and 3 inputs A, B, and C. We can state this condition or this logic function in other ways, or we can implement this logic function in other state. We can consider a memory. This is a special memory that have only 8 cells or 8. Here we have only 8 cells. And or we can say or 3 inputs for the address. 1 address line, 2nd address line, and 3rd address line. Then this memory must only have 8 cells. We can consider these 3 address lines as the 3 inputs, for example A, B, and C. And we can consider each cell of the memory as the value of logic function. For example, 1, 1, 1, 0, 0, 0, 0, and 1. Okay, now we can see that in different conditions of the inputs, we can have the value of the logic function, and we have one, yes, really we have one output, and this output is really the logic function, is really f. Then by this simple consideration, we can implement this logic function f. Then we can see that by considering or by implementation of a memory with these little inputs and these little cells, we can implement every logic function. The only thing is that we must write the values of the logic function in this memory. In FPGA, we call this memory as lookup table, L-U-T, lookup table. If, say for example, a 3-input lookup table, it means that we have a lookup table with 3 inputs, with 3 address lines. And this means that we can implement every or each logic function with 3 inputs. Now we can go to the slides. We can see that here we have 2 CLBs, 2 different FPGA cells, 2 different logic blocks. The logic block on the left side and another logic block on the right side. A logic block on the left side is older than the logic block on the right side. The logic block on the left side, you can see that 3 LUT, it means a 3-input lookup table. Then here we have a memory with 3 address lines and or 8 cells for the memory and 1 output. Then this memory can implement every or each logic function with 3 inputs, and another lookup table with 3 inputs. Thus we can implement. Then we can implement each logic function by these lookup tables. After the lookup table, we have a multiplexer and full adder. It means that it is because of this thing that in every logic works or processing works, we may have some arithmetic works, for example adding or subtraction. And we know that full adder can do our arithmetic works very simpler than logic functions. Then by a proper VHDL coding and FPGA programming, we can select or enable the full adder, and we can implement the arithmetic works or arithmetic processing better. After this, we must have a selection by a multiplexer. We can select the output of the full adder or the output of the other multiplexer. It means that we select logic operations or arithmetic operations. After this, we have a D flip-flop here. We know that in logic functions, in logic design, we have 2 different logic work. We have combinational logic or combinational circuits, and we have sequential circuits. In combinational circuits, we don't have any memory, and each output depends on the inputs at that time. In sequential logic or in sequential circuits, we have memories, and the output depends on the inputs at that time or the previous times. Okay, if we select the output from the D flip-flop, it means that we consider a memory element in our logic functions. If we select the other output from the Combinational logic, it means that we select combinational implementation for our circuits. The CLB in the right side is very similar to the left side. The only difference is that this CLB is better, is larger, and it is with higher facilities. For example, we can see that 2 lookup tables with 4 inputs than 3 inputs in this. We can see that more numbers of multiplexers for better selection between inputs and outputs. We can see that an arithmetic block that is more larger than a little full adder. We can see that 2 multiplexers at the output of arithmetic operations, and we can see that 2D flip-flops in comparison with 1D flip-flop in other logic block. 2D flip-flops for better selection. The only difference between these 2 CLBs is this. Okay, now, do you understand? All the class. Do you understand my speaking? One, two, three, 4, 5. Maybe we have some noise in the voice. Unfortunately, I think it depends on your internet line and your internet connection. As you can see, my connection is good. Connection status is excellent. Then maybe your internet connection is not so good, then you may have some noise. Okay, then we can go to other topic. We want to speak about the VHDL environment and entity and architecture. We want to speak about the entity declaration. Unfortunately, maybe, yes. Okay. Now we want to speak about the entity declaration in VHDL. At first, we must know that each entity, each system, each circuit that we want to speak about it in VHDL have 2 things or 2 kinds or 2 ways of description. What does it mean? For example, we have a system. This system has a special name. We call this system or this circuit entity. Then we have entity, and this entity has a special name. This entity has some inputs and some outputs. Then we have some inputs here and we have some outputs here. We can call them entity inputs and entity outputs, or we can say entity port. Port refers to the inputs and outputs of the system. For example, we'll speak about the input port. We say input port or output port of the system. Really, we can say entity ports. Okay. Really, okay. Yes, really. Then we have a special step. Really, we can have two steps. The first step, we must define or we must describe. We have a definition. In this definition, we'll speak about the entity name and entity ports. But what about the second step? About the second step, we must know that this system has a special structure, has a special configuration, has a special architecture. For example, we have a special architecture here. In this architecture, we have some AND gates, we have some OR gates, we have some full adders, and etc. Then when we want to speak about this system, we must specify this architecture. Then after entity, we have a special architecture here, and we must define this architecture. Really, the description of a hardware means that description about this architecture. And each architecture has a name, a special name, and some methods for describing this architecture. Okay, then after this first step, we have the second step, and in this second step, we must speak about the architecture of the system. Then we have architecture modeling or description. Okay, then the first step is definition of entity or entity definition, and the second step is about the architecture description. Okay, then now we want to speak about these main steps, and we start by the first step, entity definition. How can we define entity, or how can we define the digital system? We can start by a simple example. We consider a very simple circuit here. For example, we here have a circuit. Okay, this simple circuit is a half adder. Each half adder has two inputs, for example A and B, and two outputs. For example, we call them S and C. Yes, two inputs and two outputs. Okay, now we want to start about the definition of this system or of this circuit. We start by a keyword, entity. Entity is a keyword. Okay, entity. And now we continue with the name of entity. For example, half adder. Half adder. And we continue with another keyword, is. Okay, now we must continue with other things and another keyword, port. Port, it means that we start about inputs or speaking or writing or description of inputs and outputs. Okay, port, and we speak about the port, input ports and output ports. For example, A. What about A? A is input, then we write in. And what about the type of A? It is a bit. Another thing. B. What about B? It is input and it is bit. Another thing. S. What about S? It is output. And what about the type of this? It is bit. And the last one, C. What about C? C is output and its type is bit. Okay, this is the last one. Yes, it is output, and bit means that it is a bit number. It is only one bit number. Okay, and then another keyword. Each environment needs to end entity, or we can write end half adder. Both of them are right. Okay, this is a simple example for half adder. Do you understand? Maybe bit, maybe some bits. I will speak about some bits in another example. Yes, one of the students write a special thing, S and C, out and bit. You can write this definition in other way, like this, entity, half adder, is, port. Then now you can consider A and B, both of them with in one line. A and B, both of them are inputs and both of them are one bit number. Then you can write them in one line. And S and C, both of them are outputs and both of them are one bit number. And at the end, and as I told you, you can write end entity or end half adder. Both of them are correct. We don't have a special step that we can write all entity definition and description in one step. We can write them in two steps. The first step is here, entity definition. The second step I will told you, entity description. Do you understand? Okay. only need to write what I told you. Entity like this. No additional thing. Okay. Another example. Let me to write you another example here like this. Okay. Here we have another circuit. This circuit is very famous. It is a full adder. Or we can call this FA. It is the abbreviation of full adder. Each full adder has three inputs, A, B, and C. A, B, and C. C means that input carry. And each full adder has two outputs, S as the sum and two output. Another output is output carry. We can call this C out or CO, and I consider Z for only simplicity. It is output carry. Okay, Z is output or C out. Okay, C out. It means output carry. Okay, do you understand? Now I want to write the entity description or definition of this system. Because you know that the keyword, I don't write, for example, keyword in red line, in red color. I only write the entity of this circuit. Okay. We start by entity keyword. Entity full adder is port. Okay. A, B, and C, all of them are inputs, and all of them are one bit number. Then we can write A, B, and C. Input and bit. The other thing is about S and Z. S and Z. All of them are output, and all of them are one bit number. Okay, and full adder. And it is done. Do you understand? It is too much easy. Okay. Okay. And now let me to have another example. We can have another example here. Let me to write it for you. In this example, we consider a special system. No problem. I think these sessions are recorded and you can download them and hear my voice again. And very soon I want to upload the offline classes, and these topics will be repeated in offline classes again for you, then you can understand them. Yes. Okay. We want to consider a special system or a special circuit. This special circuit is like this. And what it is, let me to write its name and its inputs and outputs. It is a 4-bit multiplexer, a multiplier. Then it means that it takes two inputs, two 4-bit inputs, for example A and B, and it multiplies A and B with each other and produces, for example, the output, and we must know that the output must be 8 bits, then 4-bit multiplier. We'll say this, the name of this mul4, multiply 4, 4-bit multiplier, okay? And about the inputs, we have here one input A, for example, it is 4 bits, 4 bits. Another thing, another one is B, and it is 4 bits too. And another one here, for example, we here have F, and it must be 8 bits, because if we multiply two 4-bit numbers with each other, the output must be 8 bits. Okay, now we want to define or describe this system with entity. And what about this? Let's start by entity name. Entity, for example, multiply 4 or mul4. And is fourth. A and B, both of them are the same. Both of them are inputs, and both of them are 4-bit numbers. They, we can write A and B. Okay, in. And what about the multi-bit number? We can write like this. Please see this. Bit vector. Okay, bit vector. It means that we have a vector of bits, and we must specify the dimension of this vector from, for example, 3 down to 0. Okay. A and B are inputs, and they are multi-bit number. Multi-bit numbers can be described in VHDL by bit vector, and we must define the dimension of the bit vector from 3 down to 0. If we consider 0, 1, 2, 3, we have 4-bit numbers. Okay? And another one about F. It is output, out, and we must write this as bit vector. Okay, let me to write it, bit vector, bit vector. From from which to which? From 7, because it is 8-bit number, down to 0. And entity, or and mul 4. Okay, do you understand, all of you, the class? Do you understand this? Yes, let me to see you. What about 0 or 7? Consider this as A. For example, it is A. It is the 0 bit of A. A0. Okay. It is the third bit of A. A3. It is another bit. A2. It is another bit. A1. Okay. Every of these bits are 1 bit. A0, A1, A2, and A3. All of them are 4 bits. And we have a special value in this. For example, here we have 0, 1, 1, 0. Okay? You understand? Okay, Mr. Yasser, as you can see, here we have A. A is a 4-bit number. We say A 3 down to 0. It means that now I am repeating my speaking. Here we have A. A is a 4-bit number. We say that A 3 down to 0. It means that we here have A3, A2, A1, and A0 bits. For example, in this example, A0 is 0, A1 is 1, A2 is 1, and A3 is 0. It is a 4-bit number. Here we can have every value for these 4 bits. Do you understand? Mr. Muhammad Jafar. Mr. Muhammad Jafar Yasin Ash-Shabibi. Do you understand? Okay. Okay, then now we want to continue our speaking by at first going to the slide. As you can see, entity definition, entity declaration, A special example entity full adder is port A, B, C in, input, bit, S and C out, output and bit and end full adder. And another examples. Okay. And we can go to another slide. Now I want to speak about a special thing. For this speaking, let me to consider another example here, and this example is very simple. We want to consider a system like this. This is a multiplexer. Multiplexer 2 to 1. It means that this multiplexer has 2 inputs and 1 output, and we must select one of the inputs by another input, and we call this select input. Okay. Then here we have, for example, 1 input, 0 input, for example. We call this 0 input I0. Another input I1. Another input, 3 inputs really, and 1 output. This input, we call this select. Select input. We say this S. And the output, for example, F. Okay. And we want to write the entity of this system or of this circuit. It is very easy. Entity marks, for example, 2 to 1 is port I0, I1 and S. All of them are inputs. Now we want to write bits, but we can write another thing. I want to speak about it. Std Logic. What is this? The name of this is really standard logic. Std is abbreviation. We call this Std Logic. It means standard logic. Another thing is F, and it is output, and we can write standard, as I told you, logic, and then end entity. Okay, but what does it mean, Std Logic? As I told you, after the development of VHDL, IEEE supported the VHDL. And IEEE produced many libraries and packages for VHDL. One of these libraries is Standard Logic. It means that in VHDL environment we have bit. It has 2 conditions, 0 and 1, and etc. No other condition. But IEEE produces a special logic standard and called this Standard Logic or Std Logic. Okay, about this standard logic? This standard logic has many values. For example, 0, 1, and Z, high impedance. Yes, and we can have a standard logic vector. Very good. Thank you very much from your hint. Okay, 0, 1, high impedance, and etc. For example, low high. High means that here we have 1, but this one is not very good, or we can have weak high. Low means that we can have weak 0 or weak low. Another thing, X means that undefined number. Another thing, don't care. It means that we don't have a special value. You can see that we have many values here, and these are some main and famous values of standard logic. Maybe you ask me that these values, for example, high, low, X, and don't care, are not in real world. Yes, really they are not in real world, but they can help us in our simulations. Then it can be better for us if we have different simulations that use from standard logic in our description and in our simulation. Do you understand? Okay, one of the students say that I don't understand. Let me to explain for you again. If you write bit or bit vector, it means that you only have two values or two conditions, 0 and 1. And it can be sufficient for you really. If you write a standard logic, Std Logic, in your description, in your VHDL coding, it means that you can have different choices. You can have 0, 1, high impedance, don't care, high, low, undefined number, something like this. Maybe you ask me what is the difference between, for example, 1 and high. They are the same with a very little difference. 1 is an ideal one, okay? But high means that weak high or weak 1. They are really the same, but with a very little difference. And what is the difference between them? They are not in real world, but they can help us in our simulation. The only thing is that. Then if you use from a standard logic, you can have better simulation. Only thing is that. If you use from bit, you have a limitation with your simulations. Then it is better for you to use from a standard logic. And a standard logic is a package that is supported by IEEE for VHDL. Do you understand? Mr. Muhammad Jafar Yasin, do you understand? Is there any student that can translate my speakings into Arabic for better understanding? I can enable your microphone and you can translate it in Arabic. Is there anyone? Please raise his or her hand that I can enable his microphone or her microphone, and he can speak in Arabic for other students for better understanding. No one? Mrs. Marve Muhammad Jabbar. Do you have my voice? Can you speak in the class? Mrs. Marve Muhammad, can you speak? Mr. Muhammad Jafar. Let me to find for you let me Mr. Muhammad Jafar, can you speak Persian with me? Mr. Muhammad Jafar, I enable your microphone. Can you speak Persian with me?
Pardon, doctor?
Do you understand Persian?
No.
No. I want one of the students that can translate my speaking into Arabic for better understanding. I want one of the students. Yes.
Doctor. Anyone cannot translate from English to Arabic?
Okay. Then, as you can see, bit has two values only, 0 and 1. But standard logic has different values, 0, 1, high impedance, and etc. These different values are good for simulation. And standard logic is supported by IEEE. Okay, do you understand? Do you understand? Mr. Muhammad Jafar, do you understand? then I want the students to speak about these things, this standard logic, after the class in the group in System Dreng. Okay? Then let me to continue my speakings. At first, we can have 5 minutes as entr'acte and then continue speaking about the session and course. Okay, then we can have 5 minutes as entr'acte. let me to continue our speakings about the entity and entity declaration. Okay, after speaking about the entity, now it is time to speak about the architecture. This is Marve. سلام خانم مرve. سلام خالی شما خوبین؟ خسته نباشید. سلام خالی شما خوبین؟ خسته نباشید.
من دکتر شرمنده کلی دکتر.
آها بسیار خوب. خب خواهش میکنم. من فقط میخواستم همین قسمت مربوط به استاندارد لاجیک و بیت رو یه توضیح بدین برای بچه‌ها. ببینید من به فارسی هم برای شما بگم خیلی ساده هست، اصلا موضوع عجیب و غریبی نیست. بیت دو مقدار داره، 0 و 1. استاندارد لاجیک اولا اون رو IEEE درست کرده چون پشتیبانی VHDL رو بر عهده گرفته. خیلی کتابخونه‌های زیادی برای محیط VHDL. من اینا رو میگم شما باید ترجمه کنید. دست آخر همه رو با هم ترجمه کنید. کتابخونه‌های زیادی برای محیط VHDL نوشته. یکی از اینا همین استاندارد لاجیک هست. مقادیر متنوع داره، 0 1 های امپدانس. بعد نکته‌ای که وجود داره این هستش که اون مقادیر دیگه‌اش مثل HL X یا مولتیپل اونها به درد کارهای شبیه سازی میخوره، سیمولیشن میخوره. همین حالا ترجمه بفرمایید.
أساتذة يقول إنه البت مالتنا الاثنين قيم الصفر والواحد ويستخدم وهواي مكاتب بهذا الموضوع متواجد وهواي يعني نقدر نحصل على هواي مصادر بهذا الموضوع. ويقول إنه أنا حسب ما فهمت لأن صوتي يمي حيل متقطع إنه لازم ويستخدم هذا بالتشبيه أكثر شيء نستخدمه اللي هذا السايز مالته بالتشبيه.
خب حالا بپرسین دیگه همه متوجه شدن؟
يقول اكو واحد عنده سؤال؟ اي سؤال يسألونه انا اترجمه له. أساتذة أكو سؤال؟
بچه‌هایی که گفته بودن متوجه نشدیم.
ما
همه متوجه شدن.
الطلاب اللي قالوا إنه ما كانوا فاهمين هذا الموضوع افتهموا هذا الموضوع. دكتور اگر میشه من هر کلاس وارد کلاستون بشم ترجمه کنم اشکالی نیست. فقط خبر بدین که میخوام یعنی نرم بیرون کلاس.
نه فقط کلاس. خب اینو الان این 3 نفر حالا همینایی که نگاه کن نوشتن، یکی نوشته نو، یکی نوشته لا، یکی نوشته ممکنه اعاده. اینا فکر میکنم بخوام توضیح بیشتری بدیم، درسته؟
دوباره تکرار کنیم. شما این کلمه به کلمه
ببینید من اول این رو بگم. باش ببینید اول پس من خود میگم بیت فقط مقدار 0 رو حمل میکنه، این رو که متوجه
بیت ياخذ بس 0 و1. هاي اول خطوه. كل بت ياخذ بس 0 و1.
خب حالا استاندارد لاجیک مشابه بیت هست، یعنی جنس یعنی جنسش در حقیقت مشابه بیته، جنس سیگنال رو مشخص میکنه. تنها فرقی که داره مقادیر بیشتری رو نسبت به بیت میتونه برای ما داشته باشه.
الفرق الوحيد بيناتهم انه يقدر يستوعب مقادير اكبر يستوعب. يعني البت احنا قلنا 0 و1 والستاندرد لوجيك لا ياخذ اكثر من 0 و1.
به عنوان مثال همطور که گفتم بیت دو مقدار داره، 0 و 1.
طب يقول بعنوان المثال خلينا نقول البت ماخذ مقدار 0 و1.
اما استاندارد لاجیک مقادیری که داره 0
مقاديري كداره چی استاد؟
مقادیری که داره 0 1 وید یعنی های امپدانس، اچ یعنی یکی که کامل نیست، ایدئال نیست. ببینید در حوزه دنیای منطقی 1 یعنی 5 ولت. حالا اگر ما مثلا 4.5 ولت داشته باشیم به اون میگن های. 1 هست ولی ایدئال نیست. اونو با اچ نمایش داده. خب اینا رو تا اینجاشو بگیم. آره.
الستاندرد لوجيك لا ياخذ اكثر من شيء، مثل ما قال هو 0 اي و0 و1 وزيت، وهذا المكتوب هنا. يقول الاتش هو الحاله المو كامله. مثلا احنا اذا 5 بتات الاتش هنا تدل على الشيء مثلا ماخذ 4 بتات بس 4 بتات، يعني الحاله المو كامله اللي بيها نقص. مثلا وين دكتور؟
آره یا مثلا ال در حقیقت یعنی صفرش ایدئال نیست، اما صفرش ایدئال نیست.
بس الصفر المو متكامل، يعني مو البيرفكت، مو هو يعني مو هو الكامل، مو الصفر الكامل، يعني شلون نقول الواضح الصافي.
یا مثلا اون خط که هست ما بهش میگیم don't care، don't care یعنی مهم نیست اصلا، که 0 باشه یا 1.
don't care يعني هو مو مهم، سواء كان 0 القيمة كانت مالته 0 أو 1.
و X هم یعنی مثلا هنوز مقداردهی به سیگنال منطقی انجام نشده و نامعلوم هست، مقدارش تعریف نشده هست.
انه القيمة الما معلومة، انه السيجنال مالتها مو كامل، القيمة الغير معلومة، الغير مشخصة، الغير ثابتة هنقول. غير معلومة هو قال.
آره.
دکتر فقط این زیتشو من نگفتم.
حالا الان همه متوجه شدن.
حالا الان همه متوجه شدن دیگه تفاوت.
من نگفتم.
چی نگفتم؟
چی نگفتم؟
سومیه.
زد گفتم یعنی هایم.
زد گفتم یعنی های امپیدانس.
زد همون مالتها هو قالها الدكتور. نقول هسه الكل افتهم هالموضوع، افتهم هذا الموضوع الشرح؟ اكو واحد ما فاهم؟
خیلی میشه.
اكو سؤال اساتذه لو الكل افتهم؟ فهم دكتور همه فهمیدم.
بسیار عالی.
بسیار عالی. دیگه زمانم گذشت دیگه. برای قسمت آرکیتکچر انشالله جلسه دیگه صحبت می‌کنیم.
يقول المعمارية ناخذها بالدرس القادم.
خب پس اگر
دوستان دیگه سوالی ندارم که جلسه رو به انتها برسونیم.
دکتر منم خیلی مجددم دوباره خیلی معذرت میخوام. خیلی
نه خواهش
میکنم نه بچه ها اکثرا انگلیسی رو متوجه میشن. آره این مورد استثناء اتفاق افتاد. خب خدا نگهدار. خدا حافظ.